Recording, good. Now I'm sharing the screen and again opening lecture 3. Good. Okay. Whew. Yeah. Okay. So that's where we are now. We'll be starting discussing the connection of rook placement of the chessboard, rook placement of the complement, and inclusion-exclusion principles. So I cannot draw anymore, but I can use my my notes maybe instead. Okay, so here we are. Yes, so this is the example, which is example number 816 in the book. And it illustrates how one can connect the rook placements on the original board and the rook placements on the complement, plus some combinatorial inclusion and exclusion yoga. Okay, so the original problem is formulated as follows. We have two dice, one red and one green, and we are rolling them, so there is a spell. Rolls is spelled with 2L, I don't know. We are rolling them 6 times, and we want to calculate the number of, well, it says probability, but let us calculate the number of different combinations with the following properties. So there are six sides on each dice, of course, yes? And we want our a good combination for us is that we roll them, both of them 6 times. We require that each of them will show all numbers from 1 to 6. But also we don't see any combinations like 1, 2 to 1. So this stands for the red dice and this stands for the green one. So we don't see 1, 2. We don't want to see 2, 1. We don't want to see 2, 5, 3, 4, 4, 1, 4, 5, and 6, 6. Okay, so if we want to illustrate what we are doing, so we will be drawing a 6x6 chessboard. So this 6 stands for the red guy, and this 6 stands for the green guy. We want to, our good combinations would be, yeah, we are also forbidding a combination 1, 2, 2, 1, whatever. Okay, so 4, 1, 4, 5, 6, 6, 3, 4, and 2, 5. Okay. Now what we want is we want our dice to show all, each of these dice should show all numbers between 1 and 6. And we don't want to end up on these squares. What we're interested in other words, are rook placements on this chessboard. We need to place 6 rooks such that, yeah, that's exactly what we want. They should be placed in all different columns and rows, because we want all numbers to show on each of the dice. And we want to avoid those forbidden squares. So our combinatorial problem, if we forget the number with the word probability, just in terms of admissible configurations, would be, we'll be counting how many rook placements are there, of 6 rooks exactly, such that we avoid these 7 forbidden squares. Okay, so we will translate our board a little bit. So the forbidden squares will form a nicer configuration, which will be a little bit easier to analyze. And to do this, we are swapping the position 2 and 3 here. So it would be 1, 2, 4, 3, 5, 6, and we're swapping the positions which 5 and 2. Yes, 5 and 2 will be changing places, so that this thing will end up here. Okay, so now we're getting a new board, but each rook placement here corresponds in a unique way to a rook here. So counting rook placement. So this board is exactly as counting rook placements here. So it's always, if we have a chessboard, we can swap the placement of 2 rows and 2 columns. And these operations obviously do not change the rook number. Okay, now still rook placements on white squares here are quite complicated. There are many. So if we'll be trying to do it cell by cell using our inductive process, this would be nice to do on a computer, but by hands would be very tedious. So, so the book and me with the book will be suggesting a certain trick. Instead of looking on the configuration of white squares here, we'll be looking at the complementary configuration, configuration of the forbidden squares, and using certain kind of inclusion-exclusion, we'll get at the end what we want using inclusion-exclusion principle. So the first step would be to get the rook polynomial of the forbidden thing. So the forbidden thing consists of a 2 by 2 square and then 4 singletons, 3 singletons, which are disjoint. So this guy and all these guys are disjoint from each other. So the rook polynomial of this thing, the complement, is just the product of 4 rook polynomials of C1, C2, C3, C4. So these are extremely simple. This is, each of them contributes to 1 plus x. So we get 1 plus x to the cubed here. And here's also a fairly simple guy. It's rook polynomial. If we work a little bit, we'll get 2x squared plus 4x plus 1. So this 1 is always there. 4 is the number of cells. And to get positions of 2 rooks, we have just 2. One like this along the main diagonal and the other along the complementary diagonal. So this is the whole thing. So the rook polynomial of this whole configuration is here. It's just a product, such a product. Okay, now we actually want to count the number of the rook number R6 of the original thing. Yeah. And to do this, we'll use the information about the rook numbers of the complement and the certain inclusion-exclusion stuff, as I said. So let's see. So yeah. So what is it we should do? We should first of all look at all possible rook placements in the square. All possible rook placements in this 6 by 6 square, which just correspond to permutations. So, or in other words, it corresponds to throwing 2 dice, and such that each dice should go through numbers 1 to 6, and we're throwing them 6 times. Okay, so now let us denote by CI the following event. We're getting the number I on the red dice, and on the green dice, we get one of the forbidden things, one of those. So in other words, we're ending up just 1 dice. Oh, sorry. We're ending up we're in the ith row, and the j, and we're ending up in one of these 7 forbidden cells. But we're not requiring that nothing else bad happens. We're just looking at how we're counting the number of possibilities such that the ith position on the red dice correspond to a bad position on the green dice. So this would be CI. So S0 would be the cardinality. This would be 6 factorial. Now S1 would be the following thing. So we're counting how many times, so how many combinations are there that SCI happens, and we're adding them up. But I'm saying that each CI corresponds to 5 factorial. So there are 7 ways, so there are 7 cells here. We're just choosing one cell out of this. We're removing the correspondent row and column, and we're doing a permutation on the remaining 5 by 5 square. So S1, so the sum of cardinalities of the events C1 through C6, through C7, I'm sorry, is exactly 7 times 5 factorial. So there is 7 ways to place one rook in those guys, among those cells, and then the remaining would be contribution is 5 factorial. Okay. Now what about S2? S2 is the sum of number of combinations that CI and CJ happens. So they're placing 2 rooks in the bad places. We're placing 2 rooks among those 7 cells. And then we have to remove 2 rows and 2 columns. We get 4 by 4 square left, and we're doing whatever we want. We're choosing a permutation on the remaining 4 by 4 square. Okay, we know that the second rook number of this configuration is 17. Now we have to take 17 and multiply it by 4 factorial. This would be the number S2. Now the number S3, we have to place 3 rooks in this guy and cross them out, and we'll get the 3 by 3 square where we choose a permutation. So the third rook number of this configuration is 19, this guy, and this should be multiplied by 3 factorial. So S3 is 19 times 3 factorial. In similar way, so the fourth rook number of this forbidden configuration is 10, should be multiplied by 2 factorial. 5, the rook number, the fifth rook number is 2, should be multiplied by 1 factorial, and S6 is 0. Okay, now we're going back and we're thinking, so we're counting configurations where none, not C1 occur, not C2 occur, not C3, not C4, not C5, not C6. So we don't want our rook placements to end up in either of these 2 cells of the forbidden configuration. And so we're counting the number of configurations in the complement. And this we did last time. And this would be the alternating sums, sum of these numbers SIs. So we should take S0, which is 6 factorial, minus 7 times 5 factorial, plus 17 times 4 factorial, minus 19, 3 factorial, plus 10, 2 factorial, minus 2 times 1. And this gives us 192 possibilities out of extremely many. Yeah, so the probability to get this thing is calculated here. One has to think a little bit, but that's yeah, but that's this is 122. This is this 6 factorial, and then we have, I don't know where this comes from, but apparently there the sample space of all sequences of ordered pairs has 29 allowed. Okay. So this is 29 is the number of possible configurations which two dice can have, and we're throwing them 2 dice independently 6 times, and we're getting this 29 power 6 possibilities to get an ordered sequence of results of throwing 2 dice. And so the possibility to have the event which we're discussing is extremely small. It's, it's about 2 divided by 10,000. Okay, now let me end up this example, and I don't think I'll formulate this result, and I don't think I have much more to tell you. So what we just did can be formalized in the following result. So we did a particular example, but this example can be generalized into a following proposition. Let's assume that we have 2 sets, A and B. They would be finite, and the cardinality of B would be bigger. It would be denoted by capital M, and the cardinality of A would be smaller, would be denoted by N. So M would be our kind of basic set of objects, and A would be the set enumerating subsets of A. It would be the index set. So in other words, for each element A in capital A, we're choosing a subset B sub A of B. B would be our collection of objects, and A would be the index set of taking subsets. Okay, now we're counting how many choices there are, or this can be formulated as injective functions. For each element from our index set A, we want to pick a representative in B, but we don't want this representative to end up in B of A, in the subset B associated to this respective element small a in B of A. Okay, so how many choices there are to choose for each element in A, an element in B, such that the set forbidden for small a is not hit. And we're saying that this would be the number we're looking for would be equal to the alternating sum k from 1 to n. N is the cardinality of the index set, minus 1 power k. The number of rook placements on k elements on a certain chessboard C, which I'll describe in a second, times this, I call this compositions, but somebody told me that these are not compositions, these are called in the book something else. But in any case, so this number is, let me annotate, yeah, I'll do this now. So I recall that P of A and B, A is big or equal than B is A factorial, so equals A factorial divided by A minus B factorial. So A is big or equal than B. Okay, so here we have this number associated to numbers n minus k and m minus k. Why is it in this order? Should be the n should be big or equal than b. So it's probably should be, we should swap them. This should be m minus k and this should be n minus k. So this first number, at least in my convention, should be bigger than the second number. Okay, now what's the chessboard we are looking for? So the chessboard has rows labeled by elements in A and columns columns indexed by elements of B, and its squares are just pairs A and B, such that A belongs to A and B belongs to this forbidden set B of A. So if we do such a choice of a chessboard, then this formula works. And that's more or less the generalization of an example we just had. And yeah, so here is the proof, fairly short. So capital S would be our ambient space, which is the set of all injective functions from A to B. And now we denote by C sub A the condition that the image of element small a sits in capital B of A. Now we're saying that the number of elements of S satisfying at least K of this condition is the product of the rook number, kth rook number of our chessboard. That means that we're choosing K rooks, K values of small a such that the images sit in capital B of A, and times the number of injective maps from the remaining elements on n minus k elements. So we have k placements already, and we have to take injective maps from the remaining n minus k elements to the remaining m minus k elements. And then by the inclusion and exclusion principle, which we had, the number of combinations such that none of these bad conditions are satisfied. So this is the complement of C of A over all A belonging to capital A, would be then the alternating sum of these products, the rook number of this chessboard K times this corresponding P number. And this is our formula. Okay, so I think this is it for today. At least I don't have anything else special. And I just want to tell you again that the Zoom ID has been changed. Have all got the information? So your seminar would start, I guess, in something like 25 minutes. And his Zoom ID is now different. I send you an email, but I also put the new Zoom ID on the web page. So this is all for today, and I'm sorry for these technical difficulties. Okay, good. Yeah, so I'll be finishing the session, and good luck. I hope that you are doing exercises. And in general, I think I like this course. It's really, really nice.
Boris?
Huh? Yeah.
Could you upload your lecture notes for
yes,
this?
Yes. Yeah. Sure. I'll do this as well. Yes.
Thank you.
Yeah, I'll definitely do this. Okay, I'll send you the notes and I send you the link to my recording. I hope that it worked. Okay, good. Yeah. Okay, good luck. Talk to you later. Bye.